Hello and welcome to the 30th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. In the last lecture we looked at a few toy examples to get the ideas of these invariants better. Let me remind you about these invariants. These invariants were dk, which were the rank of these Hankel matrices obtained from the data, okay, and there were these rho k's which were defined as the difference in these dimensions, right, and there were these gamma k's which were defined as the difference in rho k. Okay. And what we found out from our last example and our previous discussions is that although these d's are non decreasing, yeah, these numbers rho, these invariants, they are a non increasing sequence. So, they will keep on decreasing like that, yeah, decreasing or remaining the same. And because of this reason, it turned out that we can define rho infinity, which is the limit of the sequence rho k. And the point at which this limit is achieved, that means the capital K such that the smallest such capital K such that for all k bigger than or equal to capital K, we have rho k plus 1 equals rho k equals rho infinity. This smallest such k one, that is, we call it the saturation point. Right. And then why were these numbers or these invariants and this idea of saturation important? Because we ultimately want to find out the given the data set, given this D, which is the collection of these, this trajectory that I have W0, W1, W2 and so on. From this, which I also called the trajectory W, single trajectory data. But if we have this time series and we want to identify or we want to find out the system that had generated this data, that means we want to find out the MPUM corresponding to this data. What I need to find out is the following. You see, I define this set n. We have already defined this. Let me remind you what this was. This is the collection of all those polynomial row vectors such that their action, the polynomial shift operator, polynomial difference operator acting on W produces 0. Yeah. So, this is the collection of all annihilating polynomial vectors, all annihilating polynomial vectors of the given trajectory. Okay. Now, obviously, you can easily find out that this is a submodule of this module. This is a submodule, easily found out. I have been repeating this again and again throughout these lectures. So, this is a submodule. Now, because this is a submodule, it will so happen that this submodule, because R R 1 cross q xi this is Noetherian, yeah, this will be finitely generated. Because it is finitely generated, n will be given by the row span over R psi of a certain polynomial matrix R psi, where R psi is a polynomial matrix of size G cross Q, let us say. I do not know whether I used P cross Q or G cross Q before, but it does not matter. So, such a matrix I will be able to find. Now, of course, R psi W is equal to 0. W satisfies these equations. Why? Of course, because notice that the annihilating module, the module of all annihilating polynomial vectors, is the row span of this guy, right, which in particular means that every row of this matrix, listen carefully, every row of this matrix is an annihilating polynomial vector. Because it is an annihilating polynomial vector, each row when acts on W will produce 0. So, therefore, W when R psi, let me write R sigma, when R sigma acts on W, it produces 0. Okay, fine. So, therefore, if I look at this behavior B, which is by definition kernel of R sigma, this particular R sigma, then this is an unfalsified model, because it explains the data. The model is so the data the data does not falsify this equations. So, this is an unfalsified model. This explains the data. Okay, fine. But why is it the most powerful one? That is what needs to be checked. Well, you see, suppose, so what do we have to check for this to be the MPUM? When will it turn out to be MPUM? For that, suppose we have another behavior which also explains the data. This, because our model class is such linear time invariant systems, yeah, we will it will turn out that B tilde must be equal to kernel of R tilde for some R tilde matrix. Okay. Now, because it explains the data, W must belong to B tilde, right, because it is also unfalsified, we are assuming, which would imply that R tilde sigma W will be equal to 0, which would then mean that every row of R tilde sigma, or rather every row of R tilde psi must belong to the set of annihilators, annihilating polynomial vectors. Okay. If every row of R tilde is an annihilator, that would mean R tilde psi, this matrix. So, every row of this matrix is a linear combination of the rows of R psi, because the rows of R psi generate the annihilating module n. So, therefore, that means I should be able to find out a matrix F psi such that F psi times R psi is equal to R tilde psi. Okay. But what does that mean? Notice, long before we had proven something like this, that if we have something like this, then it automatically implies that kernel of R sigma, anything that is in the kernel of this matrix automatically is in the kernel of R tilde sigma, which then means B is contained in B tilde. Remember what we started with? We started with the assumption that, okay, let us say B tilde is another unfalsified model. What we have proven is that should mean B is contained in B tilde, which means B is more powerful. So, B is more powerful than any other unfalsified model. If that is so, then that means B must be MPUM. That is the definition of MPUM. Yeah, this is the most powerful unfalsified model. Great. So, this is established that if we can find out a set of, if we can find out a matrix whose row span is this annihilating module, then we are done. But the question is, how do we do that? Yeah, how do we do that? Remember, what were we doing? We established earlier that the left kernel of the kth Hankel matrix is equal to, under the identification, of all annihilating polynomials, polynomial vectors of degree less than or equal to k. Okay. So, then if I want to find out this n in the entire n, all I need to do is I need to find out these various n naught, n 1, n 2 and so on, because ultimately as a vector space this is equal to n naught, yeah, plus n 1 plus n 2 plus n 3 and so on. Yeah, if that because of this reason we need to find out these n 0, n 1, n 2 and so on. The claim was that, you know, this obviously at the outset looks preposterous, because I cannot, you know, hope to find out all possible such nks, all possible such nks. That is impractical, to say the least, right. Is it possible to stop at some point and infer from there what will happen to the rest of these nks? As it turns out that this is the case indeed. If we go up to this saturation point, remember what is the saturation point? The saturation point is when this limit is achieved. So, the smallest value, smallest capital K, for which whenever small k is bigger than or equal to capital K, we have this, that is the saturation point. If I go up to the saturation point or beyond, the claim is that if I go up to the saturation point or beyond, yeah, and find out this guy, how can I find this out? This I can find out by finding out the left kernel of this H at capital K. If I am able to find this out, then from here I will be able to, you know, get a representation of n in terms of a polynomial matrix, as a row span of a polynomial matrix. The question is how. So, that is what we are going to do, we are going to look at carefully. So, first we start with n 0. What is n 0? N 0 of course is the n 0 are all the 0th order equations, or the 0th degree polynomial row vectors which are annihilators. How do I get this? I get this by finding out the left kernel of H naught. We may assume actually that this is left kernel is 0, we can assume that there are no first order, there are no 0th order equations, but that is not necessary. You can go ahead with situations where this is not 0, but it makes our life a little easier. So, we will just skip the we'll just consider the situation that left kernel of H naught is n naught. Now, we start, then we proceed to n 1, what we get for n 1. So, I know that n 1 will be the left kernel of H 1, right. And so, I will have a vector, I will have a matrix, R 1 whose row span over R, real row span, call it R 1, Yeah, I think I should write it like this here, R1. Yeah, row span of R1, that will be N1. This is a subspace of R 1 cross 2q, remember, because H1 is a matrix of size of 2q number of rows and infinitely many columns. So, if I want to find out things in its left kernel, those vectors will be 2q sized row vectors. Yeah, that is precisely how this R1 looks like. Okay. Now, for this R1, notice that the following also is true. R1 must actually be like this, R1 0 and R1 1. This is size q, this is size q. Okay? And we identify this R1 with R1 xi in the following manner, that this is R1 1 xi plus R0 1, right. We have seen this identification before, because this this acts on W0, this acts on W1, that is shifted version of W0. When this acts on W1, this acts on W2, that is the shifted version of W1. So, each time this guy acts on the shifted version and this guy acts on the preliminary W, right. So, that is why it is this polynomial matrix that corresponds to this constant matrix, right. So, when I identify the elements of the annihilator or the left kernel as polynomial row vectors as opposed to just ordinary vectors, yeah, this is the identification that I must do. Okay. So, that is how I get R1 xi, remember. Now, next thing that I do is, as you can expect, I am going to look at N2, right. N2 is left kernel of H2, and suppose this left kernel is going to be a subset of 1 cross 3q, right, because 3q vectors, q size 3 such row vectors of size q you have to write side by side to get your 1 cross 3q vector, which will act on this 3q rows of H2 and will produce 0. Yeah, 3q number of rows. So, it is like infinitely many columns are there, each having 3q number of entries. On those, these guys will act and will produce 0. So, it is orthogonal to all those 3q sized column vectors. That is why entries in N2 or the left kernel are elements of R1 cross 3q. But before we find out its a basis of this, we make the following observation. The moment I have found out N1 was, remember what was it? It was the row span of this matrix, right, R1 0 and R1 1. Okay. Is that all right? Notice that N2 already contains row span of, see, R01 and R11 and 0. This row span are already, because these corresponds to first order annihilating polynomials. So, these first order annihilating polynomials already are there in, because this means this N2 is all those annihilating polynomial vectors whose degrees are less than or equal to 2. So, first order means less than or equal to 2, right. So, therefore, these are there, but not just that, these things are also there. Remember the shifted version. Yeah, go back to a couple of lectures to understand why this is true. Remember that this will also be in the left kernel of H2, which is N2, right. So, this subspace is already there in N2. What I am going to do is I am going to look at this subspace, I am going to call this subspace, I am going to give it a name. I will just with a slight abuse of notation, I will call this N1 plus xi n1, right. These are the polynomial vectors which correspond to polynomial vectors here multiplied by xi, yeah, because of this shift. So, n1 plus xi n1 is this subspace. So, what I am going to do now in order to find out a basis for n2, I am going to look at n2 and I am going to quotient this guy by n1 plus xi n1, and I am going to find out a basis for this guy. Yeah, this I will assume that this is given by the row span of another matrix. I will call it R2. Yeah, this, if you do not understand quotient, just go back to your linear algebra course and try and find out what this quotient means. Essentially, if you remember the following, that is enough. This quotient means the following, that when you have this n2, n2 is actually this subspace, yeah, direct sum with the quotient. Which means you look at a basis for this guy. We have a basis for n1, we just do this shifting, you will have new vectors. They need not always be linearly independent with the old with the vectors in n1. This is the basis of n1, and that does not matter. Just look at that subspace and collect a basis for that, and then this quotient can be understood as a complementary subspace to this one, which together with this subspace gives us a direct sum decomposition of the subspace n2, right. This is true for any vector space. Whenever you have a vector space V and a subspace W, then they are finite dimensional, I am assuming. This is always true, that this is W direct sum V quotiented by W, right. That is always true. So, let me get rid of that because that is kind of peripheral. Okay. Now, once you have done that, we have this R2, right. How does this R2 look like? Notice this R2 is going to look like R2 0, R2 1 and R2 2, right, because it is 3q, q, q, q. I will identify this with R2 xi in the following manner: R2 2 xi squared plus R1 1 xi plus, oh sorry, made a mistake, terrible mistake. R2 1 xi plus R2 0, that is my R2 xi matrix, okay. Which then now means that up to n2, if I want to look at these polynomials, then every vector in n2, every polynomial row vector in n2 is actually will be contained in the row span over R xi of the matrix R1 xi followed by R2 xi. Okay. This row span only gives me n1. With polynomial, it gives me those shifted versions of polynomials in n1 which are also in n2. Yeah. Then, so for that I need polynomial linear combinations. On the other hand, just linear combinations of R2 xi will give me vectors in n2, yeah, polynomial row vectors in n2. Okay. Now, I am sure you get the trend what is happening. So, when I have this nk, I am going to look at nk as nk plus xi, sorry, nk minus 1 plus xi times nk minus 1 direct sum with nk quotiented by nk minus 1 plus xi times nk minus 1, and then I am going to find out a basis for this guy by finding out complementary vectors to this. Just do some extension, yeah, basis extensions. Standard basis extension will give you these vectors, and these vectors will be called R1 sorry RK matrix. That RK matrix is going to look like RK0, RK1 dot 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 up to RK. Okay. And then I will define RK xi to be equal to RK k xi to the power k plus RK k minus 1 xi to the k minus 1 plus dot 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 up to RK0. Okay, that is my RK xi, and I will continue it till the saturation point, which will ultimately give me this matrix R xi, which is by definition R1 xi, the first order equations, R2 xi, second order equations, so on up to RK xi. Notice that in between some of these matrices may turn out to be even 0, because sometimes this space may fill up. Yeah, just does not matter if it is a 0 row, then skip it, do not add it at all. Okay, but somehow you will get, it does not mean that there are k number of rows or whatever, you know, if each of them is P1, P2 and so on, you know, not all of. So, whenever there are 0 rows, just get rid of them, that is it. This is some matrix. I am not claiming that each of these block matrices are non-zero matrices, nothing like that. You get these matrices, if they are there, fine, if they are 0, then just skip them. That is how you form this R xi matrix, which is of course of finite size, because we did not do anything infinite, right. So, that is where we stop. Okay. This is our R xi. Now, the claim is that all of n is in fact given by the row span R xi row span of this matrix R xi. That means, the polynomial row span of the rows, polynomial linear combinations of the rows of R xi gives me all the annihilators. Yeah. Why is that so? Any annihilator which is from the construction itself, if the degree of the annihilator, so suppose we have some R xi in n, if the degree of R xi is less than or equal to capital K, yeah, which means if R xi is already in nk, then you see by the construction itself it follows that it will be a polynomial linear combination of these rows. Suppose it is not, suppose the degree is not, like this, then what happens? If I look at this R xi, yeah, it is an annihilator, and suppose it belongs to, suppose its degree, suppose the degree of this guy is some delta, right, and delta, let us say, is strictly bigger than capital K. What does this mean? Yeah, what does this mean? It means of course that R xi belongs to n delta, but if it belongs to n delta and we have already reached saturation, so for that I know that n delta is in fact equal to n delta minus 1 plus xi times n delta minus 1, right. Not just that, n delta minus 1 will actually be n delta minus 2 plus xi n delta minus 2 plus, because of this now I have xi times n delta minus 2, right. Yeah, sorry, there will be one xi and one xi squared n delta minus 2. Further on I can go even further below, because if delta minus 2 is still bigger than capital K, I will still be able to reduce it further, right, because beyond this k every n satisfies that n k plus 1 is equal to n k plus xi n k. Earlier they were just contained like this before I reach the saturation point. But beyond the saturation point, I have this satisfied with equality, right. So that is why I could do this reduction business. So ultimately it means that this n delta is going to be equal to n k, sorry, n capital K I should write, n capital K plus xi times n capital K plus xi squared times n capital K plus dot 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 plus xi to the power delta minus k in k. That is the highest degree that I get, delta. Yeah. So that is how it is going to look like, is not it? Okay. But now, so then that would mean that this r xi that I had, the arbitrary annihilating polynomial, that must be equal to some r 0 xi plus some xi into r 1 xi plus xi squared into r 2 xi plus dot 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 plus xi to the power delta minus k into r delta minus k xi, where each of these r I xi's are elements from n k. Okay. Because they are elements from n k, I know that there exists polynomial matrices f I, there exists a polynomial row vector f I xi such that r I xi must be equal to f I xi times this r xi matrix, right. Because from the construction itself we have already argued that from the construction itself everything in n k is in the row span of this guy, is in the row span of this matrix. That is what I am writing here. When I write a polynomial vector multiplying the r xi matrix, that means r I xi is in the row span of capital R xi. So now going back to this equation, what does this mean? This means r xi will then be equal to some f 0 xi into r xi plus xi into f 1 xi into r xi dot 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 plus xi to the power delta minus k f delta minus k xi r xi. Together it just means that there exists an f xi times r xi, which means r xi is in the row span over r xi of this matrix R xi. So that is what we wanted to prove, that this is what we have, n is this. So we have a description of the annihilator, and we have already proven that any matrix whose row span is the annihilator, that gives us the MPUM. So the way we have constructed, you can put it in the form of an algorithm. This is your algorithm. With this algorithm, if you follow this algorithm, you will get a polynomial matrix R xi. You will get a polynomial matrix R xi such that kernel of R sigma is the most powerful unfalsified model of the given data. Yeah, so that is where we stop for this lecture. Yeah, we have an MPUM. But we did something which was a little absurd, because we assumed that we have the full time series as the data. That is often not the case, because how can you expect to get the infinite time series as your data? The data of course will be a finite time series. When you have such a finite time series, how do you obtain, or can you even hope to obtain this MPUM that we have been claiming, is something that we will see in the next few lectures. Okay, till then, take care of yourselves. Bye.